Okay, so we are joined today by Camillo De Lellis from the Institute for Advanced Study, who will be talking about area minimizing currents mod P.
Okay, so thank you very much. I just have to tell you, I can't. It seems to be a feature of the iPad. I can't actually run this GoodNotes and Zoom simultaneously on my screen, or at least I don't know how to do that. So if you ask a question, please, rather than using the chat, just turn your mute off and just ask me a question, please. Okay, so area minimizing currents mod P. So what are they? First of all, let me tell you what are currents mod P. Okay, so P is always going to be a natural number which is bigger or equal than 2. And ideally what we would like to do is the following. So we would like to take orientable surfaces and actually integral combination of them and quotient by P copies of orientable surfaces. Okay, so let me give you a very simple example. So the Mobius band, right? So you can think about it as first of all, I have a strip, okay, and then I twist it and reconnect it in the three-dimensional space in such a way that I identify the two lines in this way. So when I do that, I can actually give an orientation to my strip, and then the boundary of the surface is going to be twice this segment here, plus, okay, something else, which is going to be like, okay, the union of this line and this line. And then mod 2, I'm just thinking that this boundary does not exist.
So did you mean one of the arrows to go the other way around?
Right. I actually mean one of the arrows to go the other way around. Absolutely. You're absolutely correct. Otherwise, I just get the usual cylinder. Right. So disappears mod 2. Okay, and I don't want to enter into technicalities, but what are actually integral currents mod P? So integral currents mod P are the closure of the objects above, which we could call sort of singular chains mod P.
Can I ask a question?
Yes.
You exactly did not want P to be, you want it to be greater than 2, and here you took P to be 2. So
oh, yes, absolutely. That's correct too. I just want to take out 0 and 1. It could be 2, yes.
Okay.
Absolutely. Although we will see later, like most of the work is actually for bigger than 2. But so but you're right. I mean, P equal to 2 is actually a perfectly legitimate and very interesting choice. So it's the closure of a singular chains mod B under area bound for the surfaces and their boundary mod P. So what do I mean by this? Well, in the case of the classical case of orientable surfaces, modulo p copies of orientable surfaces, I can define the area to be the least volume among all surfaces which are in the same equivalence class. Okay, so area mod p is equal to the least volume among all surfaces in the same equivalence class. Right, so for instance, in the case of the Mobius band, if you are like actually taking mod 2, of course you can just notice that for you S is equal to 3S mod P. And of course the same is going to be for the boundary, right? Mod 2. So of course when you're defining the area, you then want to really pick up somehow the least number, the least multiplicity that you can give to your surface in the same equivalence class. So you're not going to take, for instance, 3 times the area of the strip, but you're just going to take once the area of the strip in the case of the Mobius band. Okay, so there's actually now here an important side remark. For a very long time, so till 2018, this closure definition was the only definition available. And there's actually a very important result by Robert Young in 2018, which solved a long-standing conjecture or a long-standing open problem which roughly speaking means you can actually give a direct definition which is not going through this closure property. Okay, so direct definition through quotient of integral currents. Okay, so the way you could phrase it without entering too much in technicality is the following. You could first take classical real coefficients chain and make the closure, then make the quotient, or you can first make the quotient and then make the closure. And you could ask whether the two operations commute. And this paper by Robert Young actually proves finally that this operation commutes, which is very natural. Okay, so now what are we interested in? We are interested in area minimizing objects, or area minimizing currents mod P. Which just mean that I fix a given boundary mod P, and I look for the current mod P, which actually minimizes that one. So let me give you a very simple example. So let us take the simplest situation, which is the one-dimensional situation. Okay, so if I give you the one-dimensional situation, for instance, I can give you the following. So I can give you a bunch of points, like over here, and telling you that I'm orienting these points with like multiplicity plus and multiplicity minus over here. And then, of course, the area minimizing current, integral current, without taking any modulus is going to be this guy, the two straight lines. But it's actually going to be the two straight lines, even modulus, even if I take an integral modulus. So that's the minimizer. But now let me take the following situation. So let me take all points oriented positively. Okay, if all points are oriented positively, of course, there is not a classical surface or a classical one-dimensional object which bounds this configuration, but there is something mod 4. So I can actually take a central point, count it as 4 times the multiplicity minus, and then I can actually join these 4 points. Oops, no, that is not what I wanted to do. So here I have a plus, and then here I can actually join them in the following way. So I can do this, that, and that, okay? And you can imagine now that I can choose the location of my central connector kind of optimally in such a way that I minimize the length, right? So this is going to be a minimizer mod 4. Because the central point has multiplicity 4, but not a, say, classical minimizer in integral homology. Okay. Of course, I can do this in higher dimension too. And you can prove, and this was proved by Federer and Fleming, that there's always a minimizer so this was proved in 1960. So there exists a minimizer. And the question we are interested in is regularity.
Can I ask a question? An
Yes.
example, what would have happened if you took two points with with a multiplicity 2 and connected them to just 2 sides, and then took that mod 2? Would that also give you?
Oh, you mean if I do something like this? Let me draw a picture over here. If I do something like this. You mean? I connected to points with, like, say, here. Yeah. There will be, right. Yes, I could do that. So I'm of course connecting with 2 minus over here, 2 minus over here, but then I have to put, I don't know, 4 plus over here, for instance.
Okay, so you have to also connect the 2.
Yes, I mean, it will be impossible not to connect the 2s with something which has a 4 inside, right?
Okay.
Mod 4. And what actually happens is that this one over here is going to have more area, right? This is not convenient. This is not convenient because at all effects, you actually have a central point and just 4 connectors, essentially.
Mm-hmm. Yes. Yeah.
Okay. Right. So what I mean by 4, of course, is going to be just this red dot over here, right? So this is counted with multiplicity 4. Okay. So what is the regularity? And now let me just, see what you would naively expect. So what can you expect? So you expect some very different picture between, well, not very different, but somewhat different picture between P odd and P even. So in P odd, what you're expecting is that you have chunks of surfaces, right, which are orientable. For instance, this would be mod 3. So here you have orientable, locally area minimizing surface. So orientable minimal surfaces. Okay, and they have to meet actually somewhere together in such a way that they form a nice 3 junction. So here there's going to be like a multiplicity 3 line gamma, which of course I'm not going to see in terms of the mod 3 situation. Okay, so this is going to be the example, for instance, in mod 3. Okay, what happens for P even? Well, for P even, it's going to be kind of different. You could, of course, have the very same situation. For instance, with mod 4, you could have one central line and 4 surfaces joining, orientable, right? So that's one possibility. So it's of course, as it was happening in the even p situation, in the odd p situation. So here you're going to have 4 gamma, but that's not the only thing that might happen. Of course, it might happen that you just have a multiple copy of a Mobius strip, for instance. Okay, so you might have, okay, so this would be mod 4, but maybe there is somewhere plus, I don't know, 2 times a copy of a Mobius strip. Okay, so of course, when you're actually looking at this situation, it's clear where you have to put your boundary, which is going to have multiplicity 4. But in the case of the Mobius strip, which I'm not going to draw because I'm not actually good at drawing the Mobius strip, of course, you might choose to put your boundary sigma over here, but you might also choose to put your boundary sigma somehow over here, right? So there's an uncertainty in that. So anyway, summarizing, in the mod p case, so in the even p case, you might have unorientable pieces plus p orientable pieces. And of course, by pieces, I understand smooth pieces meeting together. And of course, some funky combination of them. And so what was known until, say, until now. So let me give you a summary of results. So first of all, mod 2 is a very nice situation. So I'm sorry, there's actually a lot of noise because some people are working right now in my courtyard, but hopefully it doesn't last long. So mod 2 is very nice because you actually know that in general, so in general, and by general, I mean in all dimension and codimension, minimizers are regular except for, so minimizers of dimension m are regular except for the set of possible singularities of codimension 2. Okay, and this is essentially of codimension 2. So in this particular situation, I can just say of dimension m minus 2. And okay, so this is essentially something that you can credit to Federer. For mod 3 and 2-dimensional surfaces in R3, there is a very nice result by Taylor saying that, in fact, this picture is precisely the picture over here. And minimizers consist locally, at least, of three orientable nice pieces meeting together on a smooth line. Okay, and this is a result of the 70s. There's another result by the 70s, and that's by White. And this is mod 4 and in codimension 1. And mod 4 and in codimension 1, he actually proves a very, very nice structural result. So, and the result is that, well, the expected picture is correct, but there's something, even something nicer that you can say. So you can say even that you can decompose, in fact, so you can decompose locally area minimizing currents mod 4 into two area minimizing currents mod 2. Okay, and let me give you a heuristic for this. So you might wonder actually why. And if you go back to the one-dimensional situation, so remember what actually in the one-dimensional situation you have. Remember that you have this toy problem of 4 points. If you have a toy problem of 4 points and you're wondering what is the central point of multiplicity 4, which I have to choose to, oops, that's not what I meant to do. Oh, wait. So if you're wondering what is actually the central point with negative multiplicity equal to 4, which is going to give you a minimizing configuration, you will actually notice that the best you can do is draw this line, draw this other line, and actually pick up as red point the crossing of the two. And of course, if you do this, you will notice that if I decompose this picture, what I'm going to have actually is one line which is going across, right over here. So this plus and this plus, which is creating a point of multiplicity 2 over here. And then there is another line which is going this way, which is also creating a point of multiplicity 2, but exactly superimposed on the red point. And this is, of course, going to give you this mod 4. So, but once you actually make this observation, of course, you observe that you can decompose your current mod 4 into two pieces which are mod 2 and are going across. And the only reason you can do that is because 4 is a sort of lucky number, right? So if I had 6, I wouldn't be able to do that. So if I had a configuration of 6 points, of course, what is going to happen is that the central guy over here, which is going to give me the minimizer, satisfies some balancing condition of some kind. But there's no reason to believe that the balancing condition is actually making this configuration decomposed into 3 segments which are going across, right? So because in general, the 3 segments which are going across are not actually going to meet into one single point, right? So if I have a situation like this, I will have created a bunch of points of multiplicity 2 over here, which are boundaries, but that will be not good somehow. So 2, 2, and 2. Okay, so now we started working actually on this on this problem sort of not long ago. So it's like a couple of years that we're working at it, and it's a bunch of people. So this is a joint work. So there is first of all a joint work, and it's actually 2 works with Jonas Hirsch, Andrea Marchese, and Salvatore Stuvard. And there is work in progress with all the 3 of them and Lucas Polaur. Okay, and what do we prove in this theorem? Oh, I actually forgot one result, which is important. So maybe before I actually state my theorem, I forgot actually another result of White. And this is important too. So this is a general paper. So this is the only result which is available for general P in codimension 1. So it doesn't say much about the structure of the singular set, but it says that the singular set has at least codimension 1. So the singular set has Hausdorff codimension 1 in the minimizer.
Can I ask you a question?
Yeah.
Sorry to interrupt. But can you explain again why for 6 it doesn't work? I'm not sure. Why didn't the picture on the right hand side, isn't that a decomposition into 3 mod 2 minimizers?
Yeah, it's a decomposition of it's a decomposition of 3 mod 2 minimizer, but it's not a current. It's not a current without boundary mod 6.
Huh, okay.
Because to be a current without boundary mod 6, you just would like to say that you want to ignore the intersection points, right?
Sure.
And the intersection points have multiplicity. Well, okay, so they are actually, sorry, they are not even mod 2, but I mean, they don't have multiplicity 2. Sorry, they have multiplicity 4.
Yeah.
Right. So the 4 points have actually multiplicity 4, and therefore I cannot cancel them mod 6, right? So they don't disappear. So if I want a minimizer mod 6, I actually have to stick really 1 point of multiplicity 6 in the middle, and I can only optimally place that one, which means I will not be able to, like, you know, make it the intersection of 3 lines.
Yeah.
Okay. Is that clear?
I think so. Yeah. Thank you.
Good. So that is actually the general theorem. And more in general, of course, you can just apply Allard, and this is a much more general theorem. So that's a consequence of the regularity for stationary varifolds. So Allard also tells you that in the most general situation, anyway, the singular set is meager, so which means it's closed and it has empty interior inside the surface. But of course, this theorem by Allard even leaves open the possibility that the singular set has positive area, right? Okay, very good. So now what is actually our theorem? So we have the following 2 theorems. So this is, say, theorem A, and theorem A says the following. So in any dimension and codimension for odd P. So the let me give a name to this picture. So let me like say this is picture A, and this is going to be picture B. So the picture A is actually correct. But so far, what we can prove actually on the intersection point, on the intersection curve, if you want, or on the intersection codimension 1 manifold of the various pieces, is that gamma is a rectifiable surface of codimension 1 in the minimizer. Okay, and this is true in any dimension and codimension. Okay, and then we have theorem B. And theorem B says for even P, and again, this theorem is valid in any dimension and codimension, the minimizer is regular except for a set, so except for a singular set of Hausdorff codimension 1. So again, in this case, I'm actually not able to give the structural result that kind of the intersection set is nice enough, for instance, to have, say, finite m-1 dimensional area, right? So notice in particular that in here, in theorem A, so in theorem A, if, say, the dimension of the minimizer is m, so the gamma has finite Hausdorff measure. Okay, I should say maybe this is interior regularity theory, so I'm not actually concerned with the boundaries. So at least far from the given boundary contour, if you have a boundary contour. Of course, there are actually interesting cases, for instance, in Riemannian manifolds in which you might have minimizers in a fixed homology class, and then you don't even have a boundary to worry about. Okay, in theorem B, that's a much more challenging problem. And what we in fact know is just that the Hausdorff dimension is m-1, but in principle, it might actually not even be sigma finite. Okay, so not even proved that gamma is sigma finite in the Hausdorff measure. Okay, so in a sense, you still would say that theorem A is not as satisfactory as it could be. So in fact, in theorem A, you're really expecting that gamma is a smooth m-1 dimensional submanifold, except maybe for some further singularities which have a smaller dimension. So gamma should be smooth. Except for some lower dimensional sets. And in theorem B, of course, at least you would like to prove that your gamma is rectifiable and has a finite m-1 dimensional measure, right? So gamma at least rectifiable and with finite measure. Okay, and the work in progress is in the following sense. So we hope of having theorem A in codimension 1. Okay, so hopefully, so let me actually call sort of this statement AS. So the strong version of theorem A and BS, the other theorem. So AS in codimension 1. So for hypersurfaces mod P. And this is, I would say, right. I mean, we're almost there, actually. So we're writing down the proof. There's a couple of details which are missing, but much more difficult is actually theorem B. And this is at least, hopefully, for two-dimensional surfaces in 3D. Okay, but this is much more uncertain. So let me, first of all, give you a feeling of why the odd, I mean, why the even situation is actually much more difficult than the odd situation. You probably got already kind of an intuition of that. And the reason why the even situation is much more difficult is because you have this second possibility. So you have this possibility of having unorientable pieces. So that actually creates a lot of extra difficulties, which the P odd doesn't have, right? So if you look at our theorem if you look at our theorem A, essentially one interpretation of theorem A is that you are actually looking at some kind of very geometrical and nonlinear free boundary problem. So one possible interpretation of theorem A is that minimizing Carlen's mod with an odd Mobius is really a free boundary problem. So that minimizing Carlen's mod 2k plus 1 is a free boundary problem. Well, what is a free boundary problem? So a free boundary problem is a typical variational problem in which you have one object which is free for you to place. So of course, the object which is free for you to place is essentially, for instance, in this picture, the central point, right? So you can actually take this central point and you can move it. And then what you're going to do, so you're going to take the minimal connection between the boundary points and the central point, and then you actually want to place your point in an optimal way, in such a way that your object minimizing the total length, right? And of course, in higher dimension, let me go back to say this picture over here. So in higher dimension, the free boundary is going to be, for instance, this portion over here. So you have these three fixed ends of the surface. So this end is fixed, this end is fixed, this end is fixed. Maybe you could even take somehow this other portion of the boundary, which is fixed. And then you have the red line, and you can actually vary the red line, and then you construct the three pieces which are sort of minimizing when you take actually that red line as a reference. And then you're free to move and to adjust the red line in such a way that you actually get a minimizer. So our theorem gives you a very, very nice interpretation of that. For P even, it's a bit more complicated because you have the unorientable, orientable, and unorientable pieces, and it's kind of, you don't exactly know how they fit together. And that is actually also the reason why it's much harder to prove regularity in that situation. Okay, so let me actually go a little bit deeper in the regularity theorem and tell you even more about that. So, so first of all, there's something which is like ubiquitous in minima surface theory, which is what is nowadays called maybe an Allard's type epsilon regularity result, or the De Giorgi type epsilon regularity result, and so now actually that it occurs to me, I think I actually cited one of the theorems incorrectly. So I gave this theorem to Brian. So for general P in codimension 1, the singular set as Hausdorff codimension in the minimizer. So wait a second. So this was actually wrong. Of course, this was not for general P, but it was for general odd P. And in fact, I will now explain it to you why for odd P, this theorem is actually much easier than for even P. Okay? Very good. So the Allard's type epsilon regularity result, which actually was predated by De Giorgi, Allard is kind of more general, is an epsilon regularity result of the following type. So it tells you, loosely speaking, so if a minimizer, is in average, and by average I just mean in an integral sense, very flat, then it is a smooth graph. So now here, maybe you should actually be a little bit more careful. So first of all, you're losing a scale. So flatness, the assumption of flatness, maybe you have it, say, in a certain ball of radius rho, centered at some point x, and then you're actually a smooth graph in half the ball. So you have to go a little bit in the interior. And in fact, in our context, it's very important to notice that flatness alone is actually not enough. So this one, it wouldn't be really the only assumption that you have to throw in. So you have to throw some more assumption for the following reason. So it's obviously, so the statement is obviously not correct mod an even modulus. So if P is equal to K, you can resort somehow to my example of having 4 points which are of the following type. So say, let me take these 2 points very close to each other, and these 2 points very close to each other. Then the minimizer is going to look like this. So it's going to be some straight line over here, and then it's going to be some other straight line over here. And you will see, of course, that these straight lines, they're actually very close to each other. This angle alpha is very, very small. And your current will look sort of very, very flat in average. So in average, very flat. but it's not going to be a smooth graph. Okay. Now, on the other hand, actually, the theorem, I mean, this epsilon regularity theorem, of course, for odd, I mean, for even p, it's going to be true if you know in advance that there's not going to be like, you know, a nasty point like this of multiplicity equal to 2k. So in other words, you also maybe have to sort of look at, so you have to look at that in this situation, not only you are very flat, but you're very close to be 2 copies of the red line, right? So close to be 2 copies of the red line. In fact, not only close to be 2 copies of the red line, but close to be 2 copies of the red line with the red line taken, though not always with the same orientation, right? So taken with, say, a certain orientation over here, because you have the 2 plus, and here you're creating the 4 minus, and here you're creating the 2 plus. So you are close to the red line, but you're close to the red line where you're actually forced to kind of change the orientation. So the situation which is really nasty is the situation in which you're very flat, but close to a non-orientable situation. So flat and close to a non-orientable guy. So going back to actually our naive picture is precisely going back to an even situation, precisely because there is the coexistence of these 2 examples. Okay, they coexist, and in a sense, not only they coexist, but you cannot really separate them in some topological way, so or in some quantitative way. So there might be a nice surface which is made by orientable pieces and is going to intersect on some segment of multiplicity 4, which is extremely close to 2 copies of the Mobius strip, in which you're actually not able to locate this kind of core blue curve for gamma in a unique way. It's like, you know, it's uncertain, or you have a freedom on where actually you can place it. So it's this degeneracy, if you want, of the free boundary problem, which is actually creating all the troubles for even p. Okay, and of course, now if p is equal to k plus 1, right, that situation is not going to happen. So let us imagine, for instance, that we want to find something which is very flat, right? And so I put a plus 1 over here, and say, let me put 2 pluses over here. Okay, and let me actually make the connector which minimizes, so the Steiner tree. Well, the Steiner tree is going to look like this. It's going to look like a very, very long line. And then at a certain point, I'm actually departing over here. I get a point of multiplicity 3. So there I have the 3 minus. But of course, this point is chosen in such a way that these angles, they're all 2 pi over 3. Okay? So in particular, if I start very flat, it means that these 2 points have to be very, very close to each other. And of course, I'm going to be okay in terms of this theorem, because I'm not insisting that I am a smooth graph all the way until the boundary of my domain, but I can actually afford to have a scale in which I'm graphical, which is smaller, right? And if I'm allowing that, of course, the flatness actually occurs at this scale. That's where it's flat. So it's in average flat. And the place where you're actually going to be graphical is this inner core. Okay, and here you are in fact graphical. Okay, so that's in a sense, why the odd P situation is extremely nice, except in higher codimensions. So this is all true. So this picture is really correct. So picture correct in codimension 1. So for hypersurfaces. But in higher codimension, there's an extra beast that you actually have to take into account. So in higher codimension, there are holomorphic subvarieties. So for instance, an object like this, z to the power 2 is equal w to the power 3, where zw are two coordinates of two complex coordinates of C2, and this I actually identify to R4. And the beast like this is actually area minimizing. And you will notice that this guy is area minimizing, but if you actually zoom into a neighborhood of the origin, you will see it's not going to be graphical, although actually in average, your surface is very, very small, right? So in a neighborhood of the origin, so ideally you would like to say that your surface is the multivalued function. So the surface is the multivalued function z goes into z to the power 3, and then you take the square root, which doesn't have a unique determination, but you know, has two branches. And this multivalued function, of course, is in a sense very flat in a neighborhood of the origin, precisely because this exponent is actually larger than 1. Okay, so hence very flat at the origin. Okay, so this was a very well-known problem in the regularity theory, even for classical surfaces, and it was addressed by Fred Almgren in his famous big regularity paper. And one way to actually go around this issue is precisely to build a theory of multivalued functions. So first step in his regularity theory is to build a theory of multivalued functions which approximate the geometric object that you have. So which approximates a minimizer at flat irregular points. Okay, so this actually was a very long paper, and it's in fact a book. It's published in the form of a 1,000 pages, almost 1,000 pages long book. And I had in the past a series of papers with Emanuele Spadaro, which actually recast this theory in a more manageable framework. Okay, so further works on Almgren's theory. And coming back actually to the area minimizing Carlen's mod P. So one of our one of the two papers with Hirsch Marchese and Stuvard develops an analogous theory in the mod P situation. So for mod P minimizing currents. Okay, so just a couple of words. So what do you mean by the fact that these objects actually approximate efficiently at flat irregular points? Well, the linearization of the area functional is the Dirichlet energy. So what you really want is, so linearization of area for graphs is the Dirichlet energy. So what you really want is a theory of multivalued functions which minimize a suitable generalization of the Dirichlet energy. And in a sense, this first theorem, I mean, this first paper over here is developing a suitable free boundary problem for multivalued graphs and the Dirichlet energy in terms of the examples that we just had. Okay, so for instance, if you go back to our situation over here, in which we were saying in here, in this picture, right, you have ideally like three pieces which are coming together, and you have this red one which is actually free, and you're trying to understand how you place the red one in such a way that you kind of minimize the Dirichlet energy, the area. You can actually phrase a seemingly interesting and simpler problem in terms of graphs which are meeting at some, you know, sort of graphs which are actually modeling pieces of surfaces which are meeting at some places, and instead of minimizing the area functional, you're actually minimizing the Dirichlet energy. And in a sense, this problem is actually easier to study than the geometric problem of area minimizing currents, and then you leverage on what you learn on this problem to actually get a regularity theory in the case of area. Okay, and let me finish with this because I think I'm actually exactly at a 1 hour time. Okay.
Thank you. Are there any questions?
Maybe, perhaps I can ask about this this last part. For multivalued mod P functions, presumably you just consider the usual multivalued functions, but you don't consider the Dirichlet energy over the multiplicity P portions. Is that right?
Right. Okay. So the way actually the thing is phrased is, so first of all, I should have been kind of a little bit more specific. So it's actually interesting so this one here is interesting for even P. Draw it this way. Okay, for even P. And the theory looks like a little bit like this. So I'm just saying P is equal to 2 times Q. And then I'm having like a function of the following type. So on top of any say point over here, so this is the domain, say. So this is the domain, and on top of the domain, I have Q values, and these Q values, they might actually have positive values, or they might have negative values. And the only way, so I will have, like, you know, down here, I will have a positive face and a negative face. And the only way actually the positive and negative face can actually meet is if they have a common point over here. So at the boundary, they all have to join together, something like that. Okay, and then I look at functions which prescribe, at multivalued functions which satisfy this requirement. And what I minimize is the sum of the Dirichlet energies of the various graphs which are on top of the positive, on top of the negative face, and the face which sort of is in between, which might have positive measure in principle. On that face, I actually measure Q times the area of the single graph which is on top of it. And so this problem is, in a sense, the free boundary problem, which is the linearization of the area functional for this geometric framework.
Mm-hmm. And so for the singular set, you minimize among like integral currents or something, or?
No, I really minimize among graphs in the sense that I prescribe. I mean, of course, you can interpret them as integral currents, but somehow they are constrained to have exactly Q points on top of each point in the domain, right? So here you're seeing the graph.
Sure.
So the red part,
the portion along which they coincide. Surely you have to vary this among some class of rectifiable sets as well, right?
Yes, the portion. So I more like think about the fact that it's some type of continuity condition on the graphs, if you want. So the portion over which they coincide doesn't necessarily need to be like, you know, only points. It could be, for instance, an interval somehow. I could perfectly envision a situation like this. So there's like a red face. Here there is a blue face. And here there's actually going to be kind of a black face, which is going to be made by a single curve. And of course, this has to have multiplicity Q dot.
Right.
And of course, what you're worried about is, like, you know, the boundary between the three faces. And in some sense, I'm not prescribing actually anything in advance on this boundary. But the regularity theory will tell you that this boundary is going to have codimension 1. And in fact, one of the things you want to do is to prove that it's a nice interface.
Mm-hmm. Okay.
Any other questions? I'll ask maybe a naive question. If you can go back to the example where you had, yes, this example with the 3 points.
Yes.
So here in such examples, what if the 2 points on the right side, if they coincide, is that allowed for them to coincide?
Yes. Of course, it's allowed, and you're going to see the degenerate. Situation of this, right? But see, somehow you are mod 3, right? So 2 points mod 3 is actually equivalent of 1 single point. So when the 2 points collapse, it is a point counted with multiplicity 2, which mod 3 is like having a point counted with multiplicity 1. And then your minimizer is just going to be 1 single straight segment, which of course is just going to be what you imagine it happens. If you're shrinking down this guy, then in this picture, if you're shrinking that down, of course, this point will just converge towards the union of the two, right? So you just see the degenerate situation of this picture, which is just going to be 1 single straight segment, which is connecting 1 point and the other point of multiplicity 2. But the point of multiplicity 2 is actually like a point of multiplicity 1 mod 3.
Mm-hmm. Okay. And another sort of limiting question, if I take in this picture one of these pluses, one of these two pluses to be have multiplicity n, and I take n to be very large, what happens then?
Okay, so now, of course, you have to change the modulus, right? So if you keep the modulus like, I don't know, 3, for instance, then automatically I will just quotient anything which is a multiple of 3 from your n, right? So it's going to be interesting only if you have a modulus which is very large.
Okay.
So one of the good things of, okay, so that's pretty much like the only advantage of working with a fixed modulus as working in the case of general integer coefficients. So if you give me whatever surface you have, I can always take away any multiple of the modulus and sort of reduce the multiplicity to be smaller than half of the multiplicity of the modulus, right? So for instance, the thing that you were saying here, when you are collapsing 2 points together, you get a point of multiplicity 2. Well, mod 3, that is like a point of multiplicity 1. So you always have the freedom of assigning multiplicities in such a way that it's a number between minus p divided by 2 and p divided by 2.
Mm-hmm.
And if you want, the unlucky situation of having p even is that this doesn't give you a unique choice of multiplicity, because if p is even, for instance, if p is 4, when you have a piece of multiplicity 2, you can assign 2, but you can assign also minus 2. And odd p does not have this freedom, right? So in odd p, the minimum number that you're going to assign is well defined. It's either negative or positive, but you never have more than one choice.
Mm-hmm. I see. Okay.
So your naive question, in a sense, is really picking up the big difference between having even and odd modulus.
Mm-hmm. Okay. Are there any other questions? Okay, if there are no more questions, then let's thank Camillo again.
Okay, so thank you very much for